There we are. And now it is. Okay. So the highs and lows of performance evaluation. So this is actually a presentation. I'm running it from the browser. So that link that you see there, the GitHub.io link, you can actually follow the slides in the browser if you wanted to do that. So let me just see if this worked. Yeah, there we are. So I will be talking about measurement, and it's kind of it's going to be fairly abstract partly, but I think it's important, and it's undervalued in machine learning. So what do I mean when I talk about measurement? Well, in some sense, we machine learners and discovery scientists, we use features all the time, and many features are measurements, right? And so we are used to performing operations on features like calculating their mean and the variance and so on. And so, but we need to be a bit careful there, because every time we apply those operations, we're assuming something about the scale of the measurement, and maybe we're doing something that's not necessarily justified. So that warrants some thought. And I will talk also more about performance metrics, and they are by definition measurements. I'm measuring how well my model performs, and so we need to clear about what we are measuring, what the properties are. Is it meaningful to take an expectation? Is it meaningful to calculate an area under the curve, and so on? So these are the kind of things that I will dig into a little bit. So what's hard about measuring? Well, in an abstract sense, measurement theory is something about the following. So we want to measure, let's say, the length of a rod A. So it's kind of, we have the real object and we map it to a real number M of A. And we typically have some kind of concatenation operation, often more than one. So for instance, if we put the two rods together, then there needs to be some kind of reasonable properties of the measurement, so that if I measure, let's say, the length of A concatenated with B, it should have some kind of mathematical relationship with the individual measurements. For instance, addition, but it doesn't have to be additive, right? And that essentially establishes a scale. So the properties of that numerical operation, circle plus, establishes a scale. So that's kind of pretty straightforward. So why is this hard? Well, before we'll look at some examples, let me also stress that if I can concatenate, I can average, right? So averaging is just saying, well, if I want the average of A and B, then I want an object C such that the measurement on C concatenated with itself gives me the same measurement as A concatenated with B, right? So, and we have different ways of averaging objects, and I will actually talk about that at some length. So let's look at a few examples. So I like cycling. It's getting colder now, but last weekend I went on 2 bike rides. Saturday, my average speed was 20 kilometers an hour. On Sunday, it was 30 kilometers an hour. Okay, so now let's put the 2 trips together. So pretend that, I continuously cycled first the first trip and then the second trip. I calculated my overall average speed as 25 kilometers an hour, which kind of may seem obvious to you because that's the arithmetic mean of the 2. But now I can actually say something about the 2 trips. So were they equally far in distance? Were they equally long in time? Were they neither? There is an opportunity for audience participation in a moment. So I'm going to answer this question for you at the moment. If I have applied the arithmetic mean here, and that tells me that actually these 2 trips were equally long in time. Whereas the weekend before, if I did 2 rides, the same numbers, but I calculated my total average speed as 24 kilometers an hour. In that case, I can conclude that they were equally far in distance. Okay, so how does that work? And let me just spell out the maths for you. It's nothing very deep, but people forget these things. So trip 1, we have distance d1, time t1, velocity is the ratio of the 2, v1. Same for trip 2. And then my overall trip, I add up the distances, I add up the times, and I have an velocity, which could be seen as an average velocity of total distance divided by total time. Now, if I do that, and I know that T1 equals T2, so the two trips took the same time, then of course I can say that the overall velocity is the arithmetic mean of the two original velocities. Okay, if I don't have T1 equals T2, then I would use a weighted arithmetic mean, right? So the weights are in red there, so it's the proportion, the proportion of total time that T1 takes, and same for T2. So those two red things evaluate to 1/2 if I have equal time, which is why I can use the unweighted arithmetic mean. On the other hand, if the distances are the same, then I'm actually can derive that V is the harmonic mean of V1 and V2, okay? But in general, I could also use a weighted harmonic mean. So the point I'm making here is that it's really about the unweighted means. If I allow myself to use weighted means, then I can use either the weighted arithmetic mean and the weighted harmonic mean. But if I use unweighted means, I'm making assumptions about either T1 equals T2 or D1 equals D2. So that's summarized here. When we average ratios, we're making assumptions. The arithmetic mean assumes denominator stay the same, which was time. And the harmonic mean assumes numerator stay the same, which was distance in our example. So alternatively, as I said, we can use weighted means, and then we can use either of them. Okay, so this is the time for audience participation. So get ready, Greg. Just give me a moment to talk through the questions, and then we can spend a minute for people to give the opportunity to answer the poll. It's an anonymous poll, so don't be worried about making mistakes, or so don't overthink it too much, but just it will be interesting to see what happens. So instead of going cycling, I'm doing machine learning. So I have two test sets, A and B. I apply a binary classifier. On A and B separately, the classifier achieves 70% and 80% accuracy, so the proportion of correctly classified instances. So now I'm going to put A and B together. This is concatenation again. I have a single test set now, and I rerun the classifier, and I get an accuracy of 75%, which is the arithmetic mean of the two things. Okay, so there are three questions in this poll, and they all look very much the same. So let me so at each question, the four options are the same. So what can I say about the two test sets? They contain the same number of instances. They contain the same number of positives, both or neither. Okay, so at least one of these answers, well, exactly one of these answers should apply. Okay, so this is question one. Question two is the same question, but now for recall. Okay, so I now have two new test sets so that there is no confusion about that. So you don't, A and B have nothing to do with C and D, but I get the same numbers out, the same average, but I'm talking about recall, which of the four alternatives apply. And finally, so recall is the true positive rate, the proportion of actual positives that were correctly classified. And the third question, question three, is the same question for precision. New test sets again, numbers are the same. So precision is the proportion of correct positive predictions. So among the positive predictions, which of them are correct? So these are the three questions. I'll leave that up here. Greg, can you start the poll?
Yes, the poll has started.
Okay. Okay, very good. Votes are coming in, still coming in. So I'll give it another minute or so. We've got nearly half of the audience has voted.
I think it needs some paper and pencil too.
It probably does. Yeah, I know. We could have played Who Wants to Be a Millionaire. I don't know if you have that in Greece, but you know, sort of this,
We do, yes.
the reward doubles every time. And then I once watched this. So this started in the UK, and the Brits are not very good in geography. So I once saw a perfect demonstration of a uniform distribution because it was some question about the capital of whatever, Turkey or whatever. And the candidate asked the audience without taking any alternatives away. So the four alternatives were there, and the answers, it was almost perfectly uniformly distributed, the answer. So it was very funny because, you know, it just threw away the the lifeline. Anyway, okay, let's stop there. We are exactly there's still votes coming in, but we're around 50% now. So I'm gonna stop there now. So I guess I
can share the results
I
now
see.
to the audience.
We're sharing it already, are we, or not?
Yes, yes.
Okay. I don't actually see it in my window here, but you can see it. Okay.
Yes, I can see it.
Right. So question one, correct answer is in red, which more than half of you had. The correct answer, they contain the same number of instances. Think about arithmetic mean needs the same values in the denominator. So in that case, that's here. In the case of recall, they need to contain the same number of positives because recall has the number of positives in the denominator. And actually, in the case of precision, this is again, the majority has the correct answer. The denominator in precision is the proportion of positive predictions made by the classifier. So if you're using an unweighted arithmetic mean on precision numbers, that needs the justification that your two models that you're comparing, or the two test set, the model makes the same number of positive predictions on the test set. So that's very interesting. I'm not sure if we are actually gonna save the results of the poll there, but oh, I can see it now here. Okay, right. Okay, fine. Okay, so let's carry on. So the correct answers were these. Indeed, if I do the arithmetic mean, then A and B contain the same number of instances for accuracy, name same number of positives for a true positive rate. And in the third case, the correct answer was neither, because neither of them is a consequence of having precision values the arithmetic mean. Okay, so what does that mean is that, so you could say this is a reason why people often in cross-validation, for example, why cross-validation, you want test folds roughly equal size, because then that justifies the arithmetic mean for accuracy. If you're doing stratified cross-validation, then that justifies averaging, doing the arithmetic mean of recall of true positive rate, and by construction also of true negative rate. But the same is not true for precision. So things are more tricky with precision. At best, if you want to apply the arithmetic mean, you need to take the relative number of positive predictions as a weight. And actually the same holds for F-score. So I'll return to F-score later. So there are some subtleties here. So it's not all plain sailing here. Okay, so this is what I'm going to talk about. So I will demonstrate, I will talk about the mathematical notion of a change of scale and how that can be useful in two cases. One of them is precision recall curves, and the other one is to understand different loss measures in machine learning. And then I will take a bit more of a higher level perspective because there are other disciplines that have thought about this, including psychology, physics, and of course computer science as well. So there are these concepts of scales and units and dimensions and types. So can we learn something from that that will be useful for machine learning? And then finally, this is sort of a much more early work. I will talk a little bit about the need for latent variable models in evaluation and also causal models, and then I'll wrap up. So carrying on. So this is a very short refresher. Many of you will know this. So if you have different means, so there's the arithmetic mean, there's the harmonic mean, there's the geometric mean, so multiplying and then taking a root, quadratic mean, like, related to Euclidean measurements, and then a generalized mean. All of these can be understood as a change of scale. So, so what you're doing is, before you take the arithmetic mean, you first change the scale through a function g, then you take the arithmetic mean, and then you apply the inverse of g to get it back to the scale that you started from. So for example, for harmonic mean, this change of scale is 1 over x, the reciprocal. For the geometric mean, the change of scale is the logarithm of x in some base. It doesn't really need to be the natural logarithm. Quadratic mean, the change of scale is squaring. Generalized mean, the change of scale is raising to the power p. As it happens, the generalized mean has all of the above as a special case. Because even the geometric mean, if you take the limit of p going to 0, then you get the geometric mean. So there is, this is not a nice framework. There are other means that have different, that are not quasi-arithmetic. But so in some sense, if we prepared, if we only want to apply arithmetic means, we should be prepared to sometimes change the scale. And then the question becomes, when do we change the scale, right? And here's an illustration. So if you look at the blue line, so all these lines, these are different means. They all go through 1, 1, because any mean says that the mean of 2 equal values is that value. So these lines connect points of which the mean is 1. Okay, so for the blue line, that is the arithmetic mean, because if I add delta to 1, then I should subtract delta to the other one to get this to get the same mean. The lowest one, the quarter circle, is the quadratic mean. The green one is the geometric mean. The red one is the harmonic mean. And actually, I also, max and min are not strictly means, but clearly the maximum. So the sort of dotted line connects point of which pairs of points where the maximum is 1. And so I put that there because that gives you an intuition that indeed the quadratic mean is sensitive to large values. And there's also the minimum line. And so means that are above the straight line for the arithmetic mean, these are means that are more sensitive to small values. And that matters, and we'll see some manifestation of that later. Of course, that can be also understood by a logarithmic transformation, for example, because clearly a logarithmic transformation is much more sensitive to small values than it is to large values. Okay, so let's look at 2 examples where these things matter. So this is, so I will first talk about precision recall curves. This was based on a paper at NIPS conference 5 years ago. So many of you will have seen this. I would be amiss if in my talk I wouldn't show at least one ROC curve. So here it is. I won't really talk about the ROC curve much, but as you know, it sort of trades off true positive rate and false positive rate, and it has all sorts of lovely properties. There's linear interpolation. You can form the convex hull. You can calculate the area under the curve. On the right is the corresponding precision recall curve. So recall, which is true positive rate, has moved to the x-axis here, and precision is on the y-axis. And these curves, people draw them, but they are really quite different from ROC curves. So for example, linear interpolation doesn't hold, and the area under these curves, although a lot of people report them, they are not really coherent things. They don't have a good interpretation. They assume linearity and so on. So there are issues with precision recall curves. And in this work, we realized that we can probably solve most of these issues by a change of scale. And here is the argument. Before I do that, I'll just remind you that the F score, the F beta score, is a weighted mean of precision and recall, which you see at the bottom there. There are lots of other ways in which you can understand the F score, but really the harmonic mean arises because we are doing an arithmetic mean in the denominator, because we're basically averaging false negatives and false positives, which end up in the denominator. Anyway, so let's have a look. What are the scale transformations that we apply? So first of all, the harmonic mean is already a bit of a giveaway. We're going to take the reciprocal. So this is the change of scale. So which means that harmonic mean on the left would correspond to an arithmetic mean on the right. But this isn't the end of the story, because if you look at these expressions, then you realize that the range of the expression on the right is from 1 to infinity. So if my true positives are 0, then I have precision is well, actually precision is technically not defined. So let's look at recall. If the true positives are 0, then recall is 0, but 1 over recall is infinity, right? And the minimum value that we can attain is 1. So we have a range of 1 to infinity, but actually the very small values of precision and recall are not really interesting. So we're going to clip that interval. We're going to cut off anything above 1 over pi. There's an argument to be made why that particular value. I'll skip that for now. So now we have a finite interval, and now we're going to just basically bring it back using the minimum and the maximum, bring it back to a 0-1 interval. And that's what we do here. And then we get these slightly odd looking expressions, which I call precision gain and recall gain. But the nice thing is that we can now do the same transformation for F score, and that transformed F score, which we call F gain, is actually now the nice arithmetic mean of precision call and recall gain. But really, what I think is a much more convincing demonstration of this is that actually, after the transformation, if we plot recall gain and precision gain against recall gain, we get the curve on the right, which looks very much like an ROC curve, and you can linearly interpolate. The area under the curve is meaningful. So this is one example where really, if we are careful, we can do much better than just plotting precision against recall and then hoping for the best. I'm not sure if, was there a question, Greg, or do I need to stop here?
There was yes, there was a question to share the point to share the slides, but Saso helped with that already. So yes, please go on.
Right. Okay, so this is just a bird's eye view on that. We can apply changes of scales, and then we can make things better by really thinking about these things. Okay, so, and there's more here. There's a link to the so behind that there's a link which takes you to let me just see if I can make that work. So there's a little web page there with the paper, and I gave a spotlight talk at NIPS about this, so there's even a video of the spotlight talks there if you want to know more about that. Okay, so that's one example. Let's look at another example where change of scale matters. So so there are different loss measures. So log loss, logarithmic loss is very popular in deep learning, but it's not the only possible choice. There are other choices like squared loss. And actually, again, and this was actually a surprise to me when I looked at this, because in cost-sensitive classification, it was very straightforward to derive squared loss, which is also called the Breyer score, as kind of an expected loss measure. But then I realized by a simple change of scale, we can actually derive log loss. And that's something that is, I think, still something that I'm still looking at in my research, how we can build on that. So I have a longer derivation in the slides, which I'm going to skip in the interest of time, but I'll give you the gist of the argument. So let C plus be the cost of misclassifying a positive. So it's a false negative because we're misclassifying it. And C minus is the cost of misclassifying a negative. So we have 2 degrees of freedom here, okay? Now, it's natural to define a number between 0 and 1, C, as the cost proportion. So it's the cost in euros or in pounds or whatever of misclassifying a positive divided by the cost in the same unit of misclassifying both the positive and the negative, okay? So that fixes 1 degree of freedom. So we still have another degree of freedom. And so one intuitive way of fixing the other degree of freedom, let's say the exchange rate, euros versus pounds, is that we kind of set a fixed budget, B, which is the sum of C plus and C minus. It's often customary to set B equal to 2, because often if you don't really have misclassification cost, then you're using error rate, in which case a misclassified positive and a misclassified negative both cost 1. Okay, so if we set a fixed budget, then we can recover C plus and C minus from that budget and the cost proportion C. But actually, this is a choice. This is a decision that our costs behave like monetary costs. And we could take a different decision. We could set a budget D, which is somehow the harmonic sum of C plus and C minus, and then we can recover C plus and C minus from D and C in a different way. So what we did in a paper with Jose Hernandez Orayo and Cesar Ferri quite a while ago, and this was published in JMLR, we asked ourselves, well, what happens if we vary C uniformly and we assume a calibrated classifier? So then the optimal thing to do is to set the decision threshold equal to C. What happens in that case? And we derived in that paper that if you follow the additive budget, the arithmetic one, the first of the 2 bullets, then we get squared loss, we get the Breyer score. But actually, if you use the harmonic budget, you get log loss. And this is essentially because 1 over x is the derivative of the natural logarithm of x, okay? Which means that I'm going to skip the derivation here, but people can look at that at their own leisure. But if you plot this graphically, if you look at the curve on the right, so essentially this is a cost curve introduced by Drummond and Holte a while ago. But the nice thing of this cost curve is that the area under the blue line is the Breyer score, and the area under the red line is the log loss. And on the horizontal axis, we have the cost proportion. The nice thing is that this immediately shows that indeed log loss is sensitive to extreme values of C, you know, which is also intuitive because there's a logarithmic, well, in this case, there's a harmonic transformation here, but remember those curves, that the harmonic curve was above the linear curve. And this actually we see in deep neural networks. Many deep neural networks which optimize log loss, they are overconfident. They are too keen to assign extreme values of probabilities because they, you know, they cost more in their model. So there is probably a lot of value in changing the loss measure, which is actually quite easy to do in many of these deep learning packages, and see if you can get a better calibrated probabilities, for example. Right. Okay. So this story is actually, I've never had the chance to write it up as more than a workshop paper, but it's out there and you can have a look at that if this is of interest. Okay, so we're half an hour into the talk, so I'm going to now move. So we've seen quite concrete examples where changes of scale can be useful. But still, the mathematical treatment of scales is quite limited because mathematicians don't talk about units, for example. They don't really talk about Celsius versus Fahrenheit. All of these are linear transformations to them, right? So there is a thing like units. There is a thing like dimensions, you know, like length is something different than mass is different, something different than volume. So I started looking into, well, there must be more theory about this. And there is, but there isn't really a definitive theory. So I'm going to give you some kind of flavor of what people have looked at and why it is probably not exactly what we want in discovery science and machine learning and in data science. So the first is something that's known as Stevens levels of measurement. This was published in 1946 in Science, so the paper is linked behind here. So the basic idea is that we have these scale types. And this is probably very familiar to machine learners. So we have nominal attributes, so just names, no order, there's no unit. And admissible transformations are, you know, you can permute, you can change the names as long as there are still, you know, the same number of names there. We have ordinal scale types where we have an order, but we don't have a unit. Okay, so it's kind of beginner, knowledgeable, expert, like in review forms, right? It's not like the difference between expert and knowledgeable is not necessarily the same as the difference between knowledgeable and beginner. So we have order, no unit. Any monotone transformation is kind of is allowable and keeps it as an ordinal scale type. Then we have interval ones where differences make sense, but I don't have a meaningful zero, right? So for example, if I measure temperature in Celsius, it doesn't really make sense to say that 40 degrees Celsius is twice as hot as 20 degrees Celsius, because it's not true in Fahrenheit, right? So we can choose our zero. The zero doesn't mean anything. So we can take ratios of differences. I can say that my body temperature today as compared to yesterday is that difference is twice as big as yesterday compared to the day before. I can say that, but that means that I'm kind of changing the scale. And finally, I have ratio scales where I have a fixed zero, and the only thing I can do is choose units. So we have the Kelvin scale, but you know, Kelvin is based on Celsius, but we could also have a similar Kelvin scale which uses the unit of Fahrenheit, right? So we still have that choice. So this is all very appealing, but this is the situation described in 1946, and we haven't really moved on from this. Plus, you can say something like, well, what are the admissible statistics in each case? Sort of, if you have a nominal attribute, you have the mode, you know, you can determine the most frequent value. If you have ordinal, then you have quantiles. If you have an interval, then you can start taking the mean and variance. Ratio scale, you can then also start multiplying things together and so on. Many statisticians think that this is too restricted because it's not kind of written in the stars that whether I can apply an arithmetic mean or a geometric mean. It's a much more pragmatic thing, right? And for example, you know, according to this story, you can't really do Spearman's rank correlation statistic, because what Spearman does is just take the ranks and then plug those into a Pearson correlation, right? So Spearman really says that differences in ranks are meaningful. So strictly speaking, you couldn't do that for ordinal data. But there are bigger problems. So there are, you know, we have many scales that don't just have a zero, but they also have a one. So for example, numbers in confusion matrices, right? They are non-negative, but they also have a maximum. We have scales with a fixed unit, maybe probability. How does that fit in? It has a zero, it has a one, but it also has a fixed unit. I don't have a Celsius and Fahrenheit scale for probabilities, right? So it's much more absolute. We have things like integer measurements. So all these things abound in machine learning, and they don't really sit comfortably in this kind of levels of measurement perspective. So there are a number of alternative proposals, but they are still very much under discussion. So that's one thing that I looked at and thought, well, there are some good ideas here, but it's not really what we need in machine learning. Then I got very excited about the physics perspectives, because physicists talk about dimensions. And actually, this goes back to Joseph Fourier. I think there is a copy here in Google Books, The Analytical Theory of Heat. And he said, it must now be remarked that every undetermined magnitude or constant has one dimension proper to itself, and that the terms of one and the same equation could not be compared if they had not the same exponent of dimension. So this was the French version of this, was written in 1822. And this theory says you have dimensions and you can only compare and add and subtract quantities with the same dimension. Or if you want to divide or multiply, then this gives you a new derived dimension, right? So pressure is something like force divided by area. And then so you end up with the dimension mass divided by length divided by time square, right? So that's this quantity here. And then we can have associated units with that, and we have choices because time we can measure in seconds, but also or length we can measure in meters, but we can also measure it in yards or feet or whatever. And that's where the Système International, the international system of units comes in, right? So this is a really compelling story. There is only one big snag here, which is that in physics, many quantities are dimensionless. So if you do something like, angle, which is a ratio of, the segment of a circle to the ratio of the circle, that gives you the angle in radians. But now you're dividing a length by a length. So you lose the dimension. You still have a unit because you can measure it in radians, or you can measure it in degrees, and you can convert between them. But sometimes units also cancel. So alcohol by volume has as a unit milliliter ethanol per 100 milliliters liquid, which basically is just a percentage. So does that mean that I can just add up alcohol by volume to anything else that is a percentage? Well, that probably doesn't make sense. And a related issue is that if you don't have polynomial, if you go beyond addition and multiplication, then you need dimensionless and unitless quantities. Otherwise, you can't coherently take the logarithm of something. And there's lots of material on the web which explains why that is. So then people say, well, in that case, if you want to apply the logarithm, you first divide your measurement by the unit that you're applying, and then you have a dimensionless and unitless quantity. But that doesn't seem to be satisfactory. So too much is lost here. So how do we build on this? So both of these perspectives have interesting features, but seem to be overly focused on somehow determining the true scale, the true dimension. And this is okay if you're Einstein and you're doing general relativity or so, but in machine learning, we need something a lot more flexible and a lot more pragmatic. Before I go on, let me ask Greg to see how am I doing time-wise?
We have 20 more minutes plus something more, so we are okay.
Okay, so I'm gonna sort of make sure that we have enough time for questions. So here is an argument. I'm gonna make an argument. Why do we need flexibility? Okay, I'm gonna make an argument that in some sense, variance is the same as entropy. Okay, this may sound really strange to you unless you're maybe a decision tree person where you think, actually, I think I've seen this before, because Quinlan uses entropy and Cart uses Gini index, which is a kind of variance, which is actually a point that I will make. But I will make a general point that from a certain perspective, these are essentially different realizations of the same thing, right? And the argument goes something as follows. it is built on the idea of a proper scoring rule, which again, some people know about this. Many people in machine learning don't know about this, and they should know about it. And it goes back to this discussion of log loss and squared loss. So there's a bit of maths here, but it's really very straightforward. So we have a scoring rule which returns the loss of predicting P for a particular class when the true class is Y. So Y can be 0 or 1, and for class 1 I predict P, and for class 0 I predict 1 minus P. And often these things have the form of a simple switch. So there is some function H, and if Y equals 1, I return H of P, and if Y equals 0, I return H of 1 minus P, okay? So this is in the two-class setting. We can do more than two classes. So then we can think about, well, what if we have a true probability Q? What would be my expected score? So what I'll do is I take the expectation, I sample Y according to Q, and I take the expectation of my scoring rule, okay? So that means that I can simply, in this form, which is linear in Y, I can just replace Y by Q. So now I have an expected score if I sample classes according to the true distribution Q, but my estimate is P. So this is a penalty term, okay? Now, we take that score, but we actually fix the 0. Effectively, we turn the scores are on an interval scale because we don't really have a meaningful 0. So we fix the 0 by subtracting the score that we would get, the penalty that we would get by predicting the true distribution, right? So P equals Q gives me this quantity here, and I'm only interested in how much the score is over that. And I call that the divergence. And then you can say the scoring rule is proper if setting P equal to Q indeed minimizes that. Okay, so we don't have negative scores, for example, and it's strictly proper if using the true distribution is the only minimizer of this. So this is why these are often called proper scoring rules. And then this term S of Q is called the generalized entropy, right? So this is not necessarily Shannon entropy, and this is not necessarily any kind of divergence that you may be thinking of, but it can be instantiated to that case. Okay, so now let's look at some actual scoring rules. So here's the logarithmic scoring rule. So H of P, we take the minus logarithm of P, and we have the scoring rule here. We have the function S. We have the divergence. Oops, that doesn't come out very well. We have the divergence, and we have the entropy. And actually, of course, now people recognize this as Kullback-Leibler divergence and Shannon entropy. But this was based on a particular choice of the scoring rule. So if I can now choose a different scoring rule, the quadratic scoring rule, and actually, interestingly, I get now something entirely different, right? So this is the divergence under the quadratic scoring rule, and this is the entropy under the quadratic scoring rule, right? So my point is, I'm not saying that Shannon entropy is the same as Bernoulli variance, but I'm saying under a perspective that matters to machine learners, we can see those as essentially having the same dimension, the same type, different realizations of the same thing. So next time you need to calculate divergence between probabilities and you reach to take the Kullback-Leibler divergence off the shelf, because that's what everybody does, stop and think for a moment and say, hey, hang on a moment, that's just a choice. I could use different divergence measures. It doesn't have to be KL divergence, all right? So I'm going to, I've got some code actually in the next slides, but I'm not going to run through this in the interest of time. But the argument that I'm leading up to here is really that computer scientists have a solution for this, and they are called abstract data types. So if we use a typed language, and in the next examples, I'm not going to run through this, but if you download the slides, then there's a link behind this which takes you to a platform where you can execute the score. And as you see, there I've used Haskell, higher order typed functional language, to basically program the equations that we had there, but we also have types here. So now we can do type inference, and that's really, I think, the computer scientists' answer to the physicists' dimensions. We want to we want to encode this in the way that suits our purposes, and you can do a different kind of piece of code if you're more interested in Shannon entropy from the perspective of information theory, where basically entropy is an expected message length, for example, an expected number of bits if you use the theoretically optimal encoding. So that gives you a different type and a different program. Okay? So my point is that maybe it's abstract data types provide their kind of relevant metadata that we want to collect about measurements. And it also, because data types are then connected to allowable operations, that gives you, I think, a really powerful framework. And I think what we should think about as machine learners is something of the kind of, what is, what would be reasonable data types? What would be reasonable operations? Can we sort of come up with a canonical set in the same way as the International System of Units has done? Okay, I'm going to skip actually the latent variable models and causal models, and I've got 2 slides to wrap up. I'm going to say this about causal models. I think ultimately in empirical machine learning, you need your experiments in your next machine learning paper should make a causal statement. You don't want to just say my algorithm beat everybody else, because that's just correlation. You want causation. You want statements of the kind, algorithm A outperformed algorithm B because the classes were highly imbalanced. Or counterfactually, if I were to rebalance the classes, I perform an intervention, then the difference in performance would disappear, right? And the interesting thing is that in this setting, causal inference is much easier than in general. Why is causal inference hard? Because I can't, as soon as I give somebody a drug, like a COVID vaccine, I can't not give the drug to the same person and see what happens, right? The interventions are not possible. But in machine learning, in these cases, the interventions are possible. I can just rerun the same experiment with rebalanced classes. So I can actually make these kind of causal statements. So wrapping up, I haven't really talked about latent variable models, but really, I think we are still in, we are a bit naive in the way that we do machine learning evaluation. We just throw the big table at the end of the paper and then put some numbers in bold, and then we say, yeah, we've achieved something here. I think that's very naive. So we need to think more about measurement theory. We also need to have models, because often the things that we're interested in are not observable. So that's where the latent variable models come in, and psychologists have done a lot of work in there, and we started using that in machine learning. And finally, really what we need is causal models and counterfactual reasons in our evaluations. Right, some acknowledgements, a lot of people that have helped me develop these arguments. And I'm going to stop there, and hopefully we have some time for questions, and then I'll also try to join the Gather platform and see if that if we can continue the discussion there. So thank you very much for listening.
Thank you very much, Peter. Let me also stop the recording.